Bismillah ar-Rahman ar-Rahim. Today's lecture is quite important actually, because we'll talk about some algorithms. For Dijkstra and bellmanford algorithms are very fundamental algorithms that are used not just for routing. They are used in different fields. The fact that you have any network and you want to calculate shortest path, whether this network is a graph or is an actual network, or it models any problem context. It models any problem context into distributed nodes, and you want to get the shortest path between two different nodes on the network. So in any case, we talked about the difference between link state and distant vector algorithms. So we said that link state uses a centralized approach where you know the state of the entire network links, and that's only facilitated through flooding. So each link state has to be flooded through the entire network, has to be sent on all the entire network, and it has to be known to every single node on the network. Okay. So every node will have to collect all the states of all the links, and then it will construct a shortest path tree, as we will see using the Dijkstra algorithm. Versus distant vector, it's a distributed approach where each node will have only the state of the links attached to it, the links that are directly connected to it. Other than that, it receives information from the neighboring nodes, and then it combines this information with the local information to be able to calculate distances between the current node and any node on the network, without really requiring global view of the entire network, right? So today, inshallah, we're going to talk about Dijkstra algorithm and bellmanford algorithm. So for Dijkstra algorithm, so it uses the link costs known to all nodes. So now we assume that we have the cost of all the, so we have the cost CXY of all the nodes in the network. So the entire network is very well known to us. And then we have a source node, and each node will have to construct a shortest path tree to all the other nodes, knowing the cost of of each link on this network. So to get to this, so first we need to run the Dijkstra algorithm, and Dijkstra algorithm will give us the shortest path tree, assuming that the source node is the root of this tree, and then the branches of this tree is all the other nodes of the network, and then this tree will give you the shortest path to all these nodes. So that will give us the dv, where v is any node on the network, and dv will give you the shortest path cost. So dv here gives you the end-to-end cost from the source node to a specific node on the network. Okay, so dv represents a path end-to-end. In order to trace yourself back, you need something to tell you that the cost from the source up to this node, you can trace it back by going to the predecessor. Okay, so once you get to the terminal node in the shortest path tree, so you can always trace yourself back by saying, what is my predecessor? So the predecessor is PV. So PV here refers to the predecessor of node V. So dV tells you the end-to-end cost, okay, given the predecessor of this node. Okay, so always you have dV with PV. Okay, dV will give you the cost, assuming that my predecessor is node whatever, node X or something. Okay, so from node V, you can trace back and go to the predecessor. From this predecessor, you calculate dv for this node, given the predecessor. And then you can trace yourself back to the source node. Okay, so that's how you construct the tree. So the way you do that is, as we will see in a minute, by trying to apply Dijkstra algorithm to get the minimum cost step by step. And once you have a link with minimum cost, you add it to a subset of nodes. So you have n nodes which constitute all the nodes in the network. You have n nodes, and you have n dash. N dash here constitute the nodes that you know the shortest path for. Okay? Because these nodes are going to be put in a pool of well-known shortest path, and then you can use it in another iteration to get the shortest path for more nodes, as we will see in a minute. And we'll see how this is done. Okay? So these are the terminology, and it's very important to understand this terminology. After doing the shortest path tree, then we can form what we call forwarding table, and we'll see. Once we have the shortest path tree, it's very, very easy to calculate the forwarding table, and then we can calculate the complexity of this protocol. So the first phase here is the initialization phase. And in initialization phase, you assume that n dash, you have the source node. So you always start from the source is using the Dijkstra algorithm. So the first phase is that you assume that you know the cost of U, and you have all the cost of all the other nodes. And then you assume that if V is adjacent to U, then you can calculate dV, the cost or the shortest. Pay attention to the fact that dV here represents the shortest cost, the shortest path cost. Okay, not the cost of is the total path cost. Okay, from U to a specific node. Okay, so initially, in the initialization phase, you can calculate dV easily of all the nodes that are adjacent to U. But the total path to all the nodes that are not adjacent to U, initially you will assume it's infinity. You will assume it's infinity. And hopefully, through certain iterations, you can enhance this infinity and get it to the minimum cost path, as we will see. So the initialization phase tells you that there are two steps mainly. First, you assume that n dash has U initially, and then the cost or dV to all other nodes can be calculated as follows. If this node is adjacent, then I can use the cost of this link as the dV. If this node is not adjacent, then initially I assume it's infinity. And then hopefully, as we go along, we can enhance this infinity to something better. So the loop goes as follows. We will take all these adjacent nodes and select the one that gives us the minimum dV. We will select the one with the minimum dV, right? And then we get this node that belongs to this path and add it to n dash. You will add it to n dash. So later on, we can say that we want the next node, including the ones in n dash, that constitute the minimum cost. And every iteration, we try to add one node such that the total dV is minimum. Okay? So for every iteration, we try to find one extra node such that the dV for this node is the minimum. And then once we find this node, we add it to n dash. And we keep doing that until we reach to all the nodes. Once we include all the nodes of the network into n dash, we stop. That's simply how it goes. Okay, so here node U. So you can assume that you run, because every node in the network will have global view, right? So you start from any node, and you can estimate the shortest path tree. Okay, so your objective now is to construct this tree here, which form the shortest path from U to all the other nodes in the network. As you can see here, this shortest path tree includes all the nodes in the network. Okay, and all the other lengths, meaning that these lengths do not or are not part of the shortest path. Okay, so from U, I want to reach to X. It's clear that I need to reach it this way. From U, I need to reach to Z. So it's clear that I need to go this and this and this and this. I don't need to go here and here. Because here, this red shortest path tree does not include this link. And the way to do this is of a specific link. Here, DV. So the way we do that is at first step, as we said, we assume that for each node, as we said, for each node we always have DV and PV. Okay? So DV is the path up to this node, and PV is the predecessor. Okay? So for this step, the predecessor is always U, right? So the cost from U to X, for example, we know it's 5, and the predecessor is U. The cost for node V, where's V? Yeah, here. The cost for node V is 7. It's adjacent. Okay? And the predecessor is U. The cost for node X is 5, as we said. The cost for node W is 3. The cost for Y, if you look at Y, Y is not adjacent in that case. So initially, we will say that dy is infinity, okay? And we don't know the predecessor, so we know it's infinity, okay? And we leave it at that, and hopefully in the next step, we will be able to enhance this, and we will see how we enhance it, okay? So this is the first step. So first step is clear, okay? So in every iteration, you add one node, okay? Then you calculate the minimum cost for all the adjacent nodes to any node in n dash. So for example, in the first iteration, we added a node W because W is the minimum out of these. You have 7, you have 3, you have 5, right? So the minimum here is 3. So node W will be added to n dash. So later, n dash will contain U and W. And then in the next step, you will try to add the adjacent node to either U or W, such that DV for any other node is minimum. Okay? So for any node that's adjacent to any node in n dash. Okay? We'll see how this is done.
Yeah, in the first iteration, you only add only one?
Yes, in every iteration you add one. In every iteration you add only one node. Okay? Type. So it's clear that between all these nodes that we need to add W. So next step we will have here, we will have U and W. Okay? And then we need to calculate the costs, the new costs, but given now that now we have W in the picture. It's not only U. So when we calculate the cost of all the other nodes, now we can see whether we can reach it from U or W. Okay? So for example, node V. Node V, the cost can be 7, or it can be 3 and 3. Right? Because now node V is reachable from W. Okay, so the new cost will have to get better time. So this is the new cost. So now we can add W, and the nodes that are adjacent to either U or W might change dV for this node. So for example, V, the cost of V now is 6, not 7, because we can reach it from U or we can reach it from V. And then in that case, we take the minimum. Okay? Type X. Well, X, we can say the cost of X is either the cost of UX or it's 3 plus 4. Right? And in that case, of course, 5 is better. And then, what about Y? Well, Y can now be W, and then 8, 11, okay, or 12, right? So Y can be reachable through here or through this link. And in that case, of course, we'll put 11, okay? Z, if we look at that, Z is not adjacent to W, and it's not adjacent to U, right? So remember, for each iteration, we add all the adjacent links to any node in N dash. ماشي? Okay? يعني we need a little bit of focus here, because these algorithms are very systematic, but you can easily get confused. And if you apply it slightly in a wrong way, خلاص, you miss it. You calculate everything in a wrong way. So you need to focus how to calculate this. So this is how to calculate dV, and of course here the predecessor is always either W or U. Here, so for example, for X, because we have reached to X from U, we put the predecessor as U. Whereas for Y, for example, we have reached to Y from W, not from X. And X actually is not part of N dash, so we cannot put X as a predecessor. So we have to put a W. Okay? And here, because it's infinity, we cannot, we don't have any predecessor. So we'll keep doing that. Of course, we'll go here, we'll go horizontal. We'll see which one is minimum. Of course, in that case, X is minimum. So we add X to N dash. So in the next iteration, it will be U, W, and X. Okay? And then we keep doing the same thing until we reach to a state that all the nodes on the network are part of N dash. But that doesn't necessarily mean that all the lengths of the network are part of N dash. You will end up with a situation that you have the shortest path tree that starts from U. That's what you need to construct. So again, here, so we add X, and then we start to have more iterations. So now you have U, and you have X, and you have W. Only now Z is becoming reachable from X. So the infinity here has become 14, which is 5 plus 9. فهمنا? So every time you calculate the cost based on the adjacent nodes to any node in N dash. Okay? مفهوم? So of course the V will stay the same as 6. There is no better. So if I go from X, the cost is definitely not better. For W, once you reach to the minimum, remember, once you reach to the minimum, you don't have to, خلاص, you reach to one node, you don't have to calculate it anymore. That's one thing that you need to notice here. Because خلاص, you added this node to the minimum shortest path tree, that's it. You don't have to calculate anymore. And X, of course, is part of, Y here is not part of N dash. So Y can be reachable from W, and it can be reachable from X, because X now is part of N dash. So we'll see the cost of Y, whether we can enhance it using the nodes in N dash or not. The answer is no. It's still reachable from W with the minimum cost, so that's why the predecessor stays the same. Okay? And now the new thing is that Z is reachable from X, and the predecessor is X with cost 14. And we keep doing that. Okay? So the next, of course, is that now we have V, because V is the minimum, and we added V to N dash. So now we have U, W, X, and V. And we'll keep doing this. So the next one will be the minimum cost for Y, because here, remember that Y has become accessible from W or V. Because V is now part of N dash. When we calculate the cost through V, we find that 3 plus 3 plus 4, so it's 10. So 10 is less than 11. So now we have enhanced the cost for Y. So, and now Y is minimum, so we can add Y to N dash. And the next one is we need to calculate for Z. So when we calculate it through Y, we add 10 plus 2, that's 12. Now we have added everything. So we have U, we have X, we have Y, we have V, we have Z, so we stop at this point. So what you have here is the shortest path tree, which does not necessarily include all the links of the network, but now you can know how to reach to any node in the network from you. مفهوم كده؟ So that's how you calculate. Of course, someone might ask, how do I estimate this cost on the link? This cost represents what from the network point of view? Well, this cost might actually include the load on this link. Very typically, it represents how much this link is loaded. If this link is highly loaded, this means that to send a packet on this node, the cost will be higher. Okay? If this node is less loaded, this means that to send a packet on this link, the cost is lower. Right? Which makes sense. Okay? And we'll see if this load is a real-time metric, which depends on the current load. That will actually introduce a very interesting issue for Dijkstra that we will talk about. So this is the exact same example on a different network. So it's another exact example of a different network, and we have to calculate the shortest path tree from U all the way to include all these nodes, and this is the shortest path tree. So the exact same steps that we have done before can be applied to this, and this is the shortest path tree, which, as I said, does not include all the lengths of the network. Once you have this shortest path tree, okay, so you can now say you don't need the costs to calculate the forwarding table. The forwarding table is the routing table. Okay, what you need here is only the shortest path tree. خلاص يعني once you calculate the shortest path tree, you don't need the costs anymore. The shortest path, the forwarding table gives you that what is the next hop if I want to reach to a specific node, right? So as we said before, forwarding is the local process, or is the local action that I have to do in order to reach to the final destination. Okay, so from you, the only two possibilities I have is either to go to V or go to X. That's the forwarding. So in order to reach to any node, I need to know whether I need to forward to V or forward to X. This is how I formulate or how I construct the forwarding table. So basically, the forwarding table is easy. So I have all the other nodes in the forwarding table. So I have V, I have X, I have Y, I have W, and I have Z. So it's very easy to figure out that given this shortest path tree, only if I need to reach to V, I need to go UV. صح? Otherwise, as you can see, UX, 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 UX.
Only show the next.
Yes, yeah, because this is forwarding. In order to go to the end path, I only need to know what's the next hop, right? And I will assume that when I go to X, X will have another forwarding table which will allow it to go to Y, and then Y will have another forwarding table which will allow it to go to either Z or W. But all these nodes, they have global view of the entire network. So when I calculate the shortest path tree, chances are all the other nodes will calculate the same shortest path tree, because we have global view, and this global view is supposed to be consistent. And as we will see, there is some limitation with this. Meshi? All right, so the procedure is systematic. So from the global view of the link state, we construct the shortest path tree using Dijkstra, which is a systematic procedure. As you can see, it's easy, but you can easily get confused and miss some calculation, in which case it can propagate, the mistake can propagate in the entire network, and the shortest path tree becomes wrong, and that can have drastic effect. So that's why you need to really focus, and you need to practice doing that. I really advise you to try 1 or 2 examples before while you're studying. Okay, so from the global view, we calculate the shortest path tree. From the shortest path tree, we can easily calculate the forwarding table, as we have done. Now we have we talk about one of the issues for Dijkstra, which is the oscillation, possibility of oscillation. This possibility of oscillation can cause you to, the oscillation is different from loops. We'll talk about loops for distant vector, but here we have the possibility of oscillation, because when one example of link state routing protocol is OSPF. OSPF uses link state, and if you need to estimate the costs based on real-time state of the network, to estimate the current load, and based on that you can estimate the cost and calculate the shortest path tree for every now and then. So for this network, for example, we need to inject 1 unit of traffic, which, let's say, like 1 packet or 1 file or something like that. Okay, we need to send it from D to A. Okay, and we need to send E unit of traffic from C also to A, and we need to inject 1 unit of traffic from B to A. Okay? So this is the current situation. So from D to A, assuming that I will send from D to A over this link. So the current load of this link will now become a 1. Okay? So the way I estimate the load is basically how much data I send. So the more data I send on this network, the higher the cost. So basically, the units of transmission are the cost. As easy as that. Okay? Okay. And C will send E traffic to A. So assuming that initially I will go from C to B and then from B to A. Now, from C to B, this link has only the traffic from C to B, right? So I will have a cost of E, which represents the amount of traffic I send on this link, right? However, from B to A, I have this 1 unit of traffic that is going from B to A, and I have this traffic that goes from C to A to A. Okay? So the cost here is 1 plus E. So مفهوم ال 1 plus E جت منين? Right? So that's the current situation of of the network. So now we have 1 and we have E and we have 1 plus E. Okay, so that's the current load. So remember here that the cost on the link is directional, which means that the cost from C to B is E. From B to C is 0. Okay? So the direction cost is different. Because it's as if I'm using 2 wires. One for one direction and another one for another direction. Okay? So the cost from C to B is E. The cost from B to C is 0. Okay? So, given this snapshot of the system, now let's see if D wants to send to A. So now D will find that the cost on this link is 1. Right? So either I send from D to A or I send this way. So let's see, from D to A the cost is 1. Right? And if I need to send from D to C, the cost is actually 0 plus E plus 1 plus E. صح? So the cost is 1 plus 2E. So which one is minimum? D to A. صح? So I will keep sending from D to A. Nothing is changing. تمام كده؟ okay. So let's see from C. When I compute here, C will find that the cost here is a 1 plus 2E. And the cost here is a 0 plus 1. Right? So which one is minimum? So 0 plus 1. Okay. So in the next iteration, C will switch the transmission to this branch instead of this branch. Okay? And not only that, before we get to this, let's see the B, what B will do, because it's more interesting. B will have from B to A with cost A 1 plus E, or from B to C to D to A. What is the cost? 1. So B will opt to use the long path given this snapshot of the system. And this assumes that all the calculations will happen at the exact same time instance. Because if C switches to send here before B calculates, B will change its decision. Okay? But the assumption here is that when we compute from here to here, all the nodes are calculating at the exact same time. Which is a very hard, because actually in practice, this almost never happens. And in fact, this oscillation has very low possibility. And in fact, they found that the network converges on its own without really having this oscillation problem. Okay? So now C will change to this branch and B will change to this branch. So the new costs will become, B will send to this branch, so this branch cost will be 1, this branch cost will be 1 plus E, and this branch cost will be 2 plus E. Okay? So it's as if all will switch to using clockwise. So all the nodes now are sending clockwise. Okay? So when you check now what is the minimum cost, you will find that D uses this branch, which is 0 plus 0 plus 0. So now D will have to choose the longest path. E will check here, it's 0 plus 0. So A will switch. And B will find that this one is also 0. Which means that all of them, if they calculate at the exact same time, they will all oscillate to use the counterclockwise. Okay? And then in the next iteration, they will go clockwise. And then they will go counterclockwise. So this is with the assumption that, again, there are two assumptions here. One assumption is that all the nodes perform the computation at the exact same time. The other assumption here is that the cost of the link is unidirectional. So the cost for one direction is different from the cost in another direction. Okay? So the cost this way is different from the cost this way. ماشي? Those are the two assumptions. And this oscillation problem may happen using those two assumptions. Okay? This is what we call possibility of oscillation. The good news is, as I said, in practice, you can almost never synchronize the computation. So the network actually converges on its own without any problem. And of course, this is proven by some experimental work, and they have found that there is no possibility of oscillation, and the possibility of oscillation is almost 0. Okay? Type. So this is the link state that uses Dijkstra algorithm, and we have discussed the Dijkstra algorithm and the possibility of oscillation. Any question at this point? So this is the first part of routing. So the distant vector, as we said, for distant vector, we use bellmanford. Bellmanford is a distributed algorithm. So there is no centralized computation. There is no concept of constructing shortest path tree because you don't have global view. You don't have global view. Okay? So Bellmanford uses the concept of dynamic programming. Dynamic programming, by the way, is one of the very, 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 very efficient techniques, which is based on recursion. Nestle Khadu programming, do you know what recursion is? A recursion here means that I will find the minimum cost path by dividing the problem into the cost, what I know, okay, versus the possibility of unknowns. So the cost of y, the cost from x to y. So the subscript here is the source. So the source, the cost from x to y, and here we call it distance. Because as we said, we don't have all the states of all the links on the network. But we need to estimate the distance. Okay? So the estimated distance between x and y is based on what I know at the moment, okay, which is the cost from x to any node v that's adjacent to me. That I know. Okay? Plus the distance from v to y. Okay? So if for example, I need to calculate the distance from x to y and y happens to be an adjacent node, so basically this is the cxy plus the distance from y to y, which is 0. Okay? If I need to calculate the distance between x and any other non-adjacent nodes, then I need to take one of the intermediate nodes that's adjacent to x and then use it as a state to reach to y. And then try to see what is all the possible combinations, what is the adjacent v that will give me the minimum cost. But remember here, I have the cost for all the adjacent nodes, but I don't necessarily have the distance between these adjacent nodes and all the other nodes. So what do I do? Well, what happens here is that you wait for the other nodes to send you the distances, the estimated distances from their side. Okay? And then whatever they send to you, you can say, is this better than what I have? Which means that the distance they can send me, okay, is better than what I have? If the answer is yes, then you use it and you decrease the distance between you and this node, which means that the adjacent node will change. Okay? If the distance that they give to you is worse, then you stay on what you have. As easy as that. Okay? This is a distributed algorithm in nature, and the good news is, with this very simple concept, the network will converge. There is a proof of convergence, and you have a guarantee that the node will in fact converge. Of course, there are some issues with that we will discuss, but in general, the node will converge. But remember that this is not a centralized approach. Each node will have only local view of all the adjacent nodes, and then it receives distances from all the other nodes. But it doesn't have state. It doesn't have the states of all the links. So if you have a network like this, so you have nodes like DV, Z. So remember, V, X, W, these are V, X, and W. Okay? These are adjacent nodes to you. Right? Okay? So here, we assume that we can calculate these distances. Of course, we can calculate it visually because we have global view of this network. But you does not have this global view yet. But we will show you how recursively you can estimate these distances. So initially, we will now try to accept the assumption that dvz can be calculated. So v from V to Z is either to go UWZ, which is 8, and that's of course not the minimum, but you can go V, X, Y, Z. This is 5. Okay? And XV, from X to, so for X to Z, this is clearly 3. And from W to Z, this is clearly 1 and 2. Right? So, again, we did not estimate this based on bellmanford. Okay? Bellmanford will have to run for different iterations until it estimates this. But assuming that we can calculate this. So now, what we could do is that we can say the cost of U from U to Z is basically based on the cost that I know from U to all the adjacent nodes plus these distances. Okay? If I know these distances, which means I receive them from V, X, and W. They have given that to me. If I have this information, then I can calculate the distance to Z by saying the distance to Z is either the cost of UV plus VZ, or the cost of UX plus XZ, or the cost of UW plus WZ. And these costs, I know, or assume that I know. Right? So I can put this equation like this, and then I can calculate UV plus VZ, UX plus XZ, UW plus WZ. And then the distance from U to Z is the minimum of these. Okay? So of course the minimum of these is 2 plus 5, 1 plus 3, 5 plus 3. So I get the calculation 7, 4, and 8. So the answer is 4. Which means I need to go through X. Which means X, Y, Z. And this is in fact the shortest path from U to Z. Okay? So this network is complicated. And what you are trying to do now is to break down the problem. That's what dynamic programming helps you to do. Dynamic programming helps you to break down the big problem into smaller problem. One of these problems you have the answer for, which is the adjacent nodes that are attached to you, so you know the code, so that's easy. And then the other part is definitely a less problem compared to the bigger problem. So try to solve this a less complex problem. And then you get this complex problem and you divide it into another two sub-problems. One of them you know the answer for, and the other one. So every time a node sends you the distances, this is an answer that you can group and try to answer the big problem that you have. And you can do this in a distributed way using this dynamic programming. So in order to do that, you need to estimate the distance between x and y, where x is the source and y is any node in the network, by receiving distances from all the adjacent nodes, and then you can calculate the minimum cost to a specific node by trying all the adjacent nodes and then find the adjacent node that gives you the minimum distance. And this adjacent node will be the one that you use in the forwarding table. Okay? Because this is distributed, we will see that the node itself is small, but the iterations are not that easy. So the basic idea here is that from time to time, each node will calculate the distance between itself and all the adjacent nodes. Okay? So the distance from x to y, and where x is the root node and y is any adjacent node. Send these distances to all the neighboring nodes. These neighboring nodes will use this cost to calculate the distance between itself and any other node in the network, and then selects the one with the minimum cost. And this way is distributed. But remember here that you have distances, but you don't have states of the links. So you have a lump sum of distances between nodes, but you don't have the individual state of the links. And that's the main difference between link state and distant vector. Okay? One thing we need to know here is that this distant vector algorithm is iterative. Iterative means, or iterative always indicates you don't know when it converges. Okay? You receive distances from the neighboring nodes. You calculate the minimum distance based on what you receive and what you have. Okay? But you don't know when the convergence is going. The convergence happens when? The convergence happens when every time you receive certain distances, okay, what you have is always better.
Better than the previous one.
Or there is no enhancement compared to what you have. Okay? So in that case, you stop. When you stop, you can get triggered again only when the cost on one link changes. When the cost on one link changes, then the node attached to this link needs to inform all the other neighboring nodes, and then you trigger bellmanford again until you reach to the steady state that whenever you send these distances to all the other neighboring nodes, the nodes find that what they have is better or is the same, so there is no improvement, so they stop. Okay? So iterative means in complexity analysis, when the algorithm is iterative, it means that you cannot evaluate or you cannot estimate the complexity, because you are having iterations but you don't know when the system is going to converge. Okay, so sometimes people look at iterative algorithms as inefficient, but in fact, in many cases, they are more practical. Okay, طيب. So the way bellmanford works is that you wait until the cost of one of the links adjacent to you changes. When does this link cost changes? If this link gets more load, if the computer that's connected to this link is down, is up, changes its bandwidth, something like that. Okay, some change happens, the cost on this link changes. Then, in that case, you need to re-estimate the distance and send it to all the neighboring nodes. Okay. Then you need to recompute the estimates, and if distance of the new destination changes, then you send to others. Okay. Sometimes you estimate and you find that the estimated cost end to end does not change, which means that even though one of the links is down, but this link will not affect the end-to-end path because I can still reach to the same destination using another link. And this other link is still belong to the shortest path anyway. So in terms of end-to-end distance, there's no change. So in that case, I keep the distance as is, and I don't have to send it to others because it did not change. Which means that this recomputation is triggered when the cost changes. Okay. Of course, distant vector routing protocols, they have two schools. One school is RIP, or routing information protocol. Routing information protocol uses the concept of proactive, which means that whether the link cost changes or not, I will send periodically. I will have to recompute periodically. خلاص. And this is the simplest way. So either it changes or not, I will have to recompute. But of course, this will have extra overhead because you recompute unnecessarily, even though the network did not change. Another approach is the EIGRP, which uses the triggered approach. Only if a link cost changes, then it gets triggered and recomputes the new costs and send it to the neighboring nodes. ففهمنا هو الأول احنا بنتكلم على technique. So first we talk about techniques, which is based on algorithms, and these algorithms in the link state they use Dijkstra, in the distant vector they use bellmanford, right? And then routing protocols will have to use these techniques in a specific format, and this specific format is that these routing updates happens periodically or trigger based or something like this. So this is the difference. These are the differences between the different protocols. But many protocols may select or may opt to use the same algorithm or the same technique. ماشي؟ طيب. So that's how. So again, we look at every one of these separately. Okay. So this is the table at X. So initially the table at X is as follows. I know the cost from X to the adjacent nodes. So from X to Y is 2. From X to Z is 7. Okay? And from X to X is 0. تمام?
But here is taken x to z is equal to 3.
Sorry? From X to Z. No, but it's adjacent. So first I'll have to take the adjacent cost. So initially, of course, what you said is true. So the distance between X and Z is 3. I know it's 3 because I can see it. But this is because you have global view of the network. X at this point doesn't have global view of the network. Okay. When does it know the global view of the network? When it receives information from Y or from Z that the distance between Y and Z or Z to Y is 1. This information is where? This information is here. Y has a distance to Z of 1. Y has a distance to itself of 0, and Y has a distance to X of 2. But X doesn't know this information. So X will have to put everything as a infinity, because it doesn't know the what is the information coming from Y. Initially, it doesn't have this information. Then what happens is that Y will send all these distances to X. X will take these distances and then will use it to estimate the new distances based on the information from Y. Okay? So first, this is the information from X, which is known to X. This is the information from Y, which is not known to X initially. This is the information from Z, which is also not known to X initially. Okay? So in the second iteration, Y will send all its distances to X, and Z will send all its distances to X. So X will now have all the information from Y and Z. And now, X will have to recompute this based on the information of from Y and Z. So let's see. So the cost from X to X is 0, and it cannot be enhanced more than this. The distance between X and Y is the cost from X and Y plus the distance between Y and Y, which is 0. Okay? Or the cost from X to Z, which is 7, plus the distance from Z to Y, which is 1. Okay? Okay? So it's 7 plus 1, it's 8. So, of course, this cost will stay the same. Okay? And now, cost from X to Z is either the cost from X to Z, which is 7, or the cost from X to Y, which is 2, plus the distance which I received from Y to Z, which is 1. And of course, the 7 here will become 3. Okay? So here, only the cost from X to Z has improved. Remember, here X will have to send to Y the same thing. So this cost will have to go to Y. And will have to go to Z. And of course, the Y will have to go to Z as well. So the same process that we have done here will happen at Y and X independently, because this is distributed. ماشي؟ مفهوم? Okay. So we'll keep doing that. So this cost, as I said, is the cost from X to Y plus the distance from Y to Z, or the cost from X to Z plus the distance from Z to Z is 0. So we find that this cost is better, and the cost has been updated to 3 instead of 7. Okay? And you will end up with something like this. So it's so if you notice here, the only thing that has been updated in this table is the fact that the cost from Z to X, from Z to X is along Y, which is also a 3. So in this iteration, once you reach to this iteration, assuming that you receive any information from Y and Z, you always converge to the same, as you can see, all these matrices are exactly the same, which means that whatever information you will receive, it's exactly the same of what you have. So you will not have to recompute anymore, because you cannot improve over what you have at all. So that's when you reach the state of convergence. So now once we converge, you have converged here through 3 iterations, but remember, because we have only 3 links, so imagine if you can do this on a very large network. Yani, you can imagine that it's very complicated. However, remember that the computation is happening at every node independently from all the other nodes. So from each node point of view, this is what it has to do. So in terms of computation, it's reasonable. Because I don't have to do all of this. I have to do this only. So X has to do this, Y has to do this, and Z has to do this. So, and here I converged within 3 iterations. Of course, I would imagine that if the network is larger, I will have to spend more iterations. But because it's actually distributed, still the computation overall is reasonable. Okay. So one thing we need to discuss here is, and this requires a little bit of focus.
If there are n nodes, then we need n iterations.
Not necessarily, no. We will discuss this now. And I will show you that the number of iterations does not necessarily depend on the number of nodes in the network. They depend on the cost and the correlation of the cost on the links. So here we need to show how the distant updates work when the cost on one link changes. Okay, so what if the node changes its cost to a better cost? And what if the link cost changes to something worse? The rule of thumb here is that for distant vector protocol, good news travel fast, bad news travel slow. Okay, so this is the summary of this. Good news travel fast, which means that if the link cost improves, the conversions will happen very fast. If the link cost worsens, okay, we will see the effect of this. It's very interesting. The effect of this will be kind of interesting, because this bad news will travel in the network in a very slow way. We'll see how this happens. So a node detects the local link cost change. So if X has one link here, and this link cost changes to something better, or the cost reduces. Okay. So I need to update the routing information, which means that X will have to update the distance between X and Y, and will have to inform Y, and will have to inform Z. صح كده؟ Okay. If the distant vector changes, we have to notify neighbors. So at time t0, Y detects the link cost change and update its distant vectors. So Y will have to update its distant vector. So the distant vector from Y to X, it has improved, because the distance from Y to X is either 4, and now it's become 1, or 1 plus 50, which is 51. So the distant vector is now, instead of 4, it becomes 1, which has improved. And this distant vector changes. It changed it to something better, but it changed it. So in that case, I have to inform others. So I have to inform X that the distance between me and X is now 1. The interesting thing here, when I inform X that the distance between Y and X is now 1, X doesn't have any information whether this is by going from Y to X or by going from YZX. And again, this is because I don't have global view of the network, right? And this is the main difference. This is the actual main difference between link state and distant vector. Okay? So for X, although X can get triggered of of this cost that it has reduced, but X doesn't know whether Y wants to go to X through Z or direct through X. It doesn't know. Okay? So, so at time 0, Y will detect the change and will inform X and will inform Z. So Z will see, so if I want to reach to, so Z will see update from Y and update its table, computes the new least cost to X. So now the least cost to X is either going through Z, which now has changed to 2 instead of 5, which means that the distance between Z and X is now changed to 2 instead of 5. So Z will have to send the new distance to Y and X. Okay? And also, and sends its neighbor the dv, the distance vector. At time t2, Y receives Z's update. Remember, because Z finds that the cost to X is changed. So Z will send to Y, and Z will send to X. Okay? So at time t2, Y sends X update, updates its distance, and Y's least cost don't change. خلاص, because Z, when it sends to Y, Y will find that the cost to Z is either 1 or 1 plus 50. So it's definitely 1, which is exactly the same. Right? And X will see the cost to Z is either through Y, which is 2, or through Z, which is 50. So it will stay the same. Because this information Y has already received from Y and it updated its own distance. So in fact, through 2 iterations, the network converged. صح? So this good news has traveled and the convergence happened and there's no change after 2 iterations only. So it took me 2 timestamps or 2 time slots to reach to conversions. And that's relatively fast. And that's because of the fact that the link cost on one of the link improved. So let's see بقى when the cost on one of the links gets really worse. Okay? So that's the interesting.
The number at T2 will change. And it's become high cost.
Y? Y receives from Z the update. And the update here is that the cost...
In case of when the cost will increase, not decrease.
Yeah. Okay. Well, that's what we want to... Okay. So this is the other scenario. So the bad news here, travel slow. So here, أنا مش عارف ليه ما جاتش الابديت. أنا المفروض إن I have updated that. So here it's this is 50. So this cost is already 50. And the cost from X to Y has now changed to 60 instead of
4.
Instead of 4 or 1. So now it has become really worse. So the good news travel fast. However, let's see. When Y detects this link change, Y will send the change that the cost from Y to X now has changed from 4 to 60. Okay? So Y will have to now send the cost because Y again does not have global view. Y will change this dv to X. So distance of Y to X has now become 60. And it will send this new distance to Z and to X. To Z and to X. Okay? So X will now say, okay, I have the cost from Y, which is dyx 60. So I see from X to Y is either the distance from Y to X. So the distance here is from X to Y is either through y, and through y is 60. Okay, or the distance from z from x to z plus dzy. Okay, so the distance from x to
Yes, from X to Z.
so the distance between x to z is 50 plus dyz. From the distance between so the cost from x to z plus dzy, صح? Which is a 50 plus 1, or the distance between x and y, which is 60. Okay, so in that case, the distance between x and z will become 51. Okay,
X to Y.
the distance between x to y, sorry, will become 51, and y will send to z the fact that dyx is 60. So z will have to calculate dzy, dzy is 1, sorry. Dzy is either the cost from z to y plus dyy, or the cost from z to x plus dxy. صح? The cost from z to y is 1 plus yy is 1.
Zero.
And the cost from z to x, the cost from z to x is 50 plus dxy is 60. So the cost will become from z to y will become لا في لخبطه انا متلخبط هنا
50 plus 60, 100.
Yes, correct.
ايوه from z to y it will become 1 صح؟
Yes.
1 or 60.
هم؟
110.
Yes, correct.
ايوه will become y بس هو ده لا مش ده اللي احنا عايزينه احنا بس في لخبطه هنا. at time 0 dzx هي البتاعه دي عامله لنا مشكله. التشينج ده عامل مشكله شويه. لا في لخبطه هنا. طب خلينا ثانيه واحده.